Fred, have you went to the Galaxy Coaster in LA County Fair?
Galaxy Coaster? It sounds familiar.
It's a really fast one.
For real?
Yeah.
Should I? Dude, I'm kind of scared of roller coasters though.
They tryna be crazy.
I think it's
They
safe
tryna be
though.
crazy.
I mean,
She wanna be crazy.
I always wonder how the science behind it works, you know?
That's true,
That'd be
yeah.
crazy. I wish we could find out.
Oh my God. Of course it's safe. I'm gonna take you to the lab and prove it to you with science.
Welcome to the lab. In order to prove the safety of this roller coaster, we built it to scale model. At this point, the potential energy of the marble that is rolled through is 64.29 joules. At our point A, according to the law of conservation of energy, when plugged into the formula, the theoretical velocity of the ball should be 4 meters per second. After finding the theoretical velocity at point A, which is 4 meters per second, we must then find the theoretical velocity of point B, which is after the loop. After doing the math, this theoretical velocity is determined to be 2.06 meters per second. Of course, this is theoretical and does not account for friction. The real velocity at this point, through the use of photo gates, was determined to be 0.5 meters per second. Pretty crazy. After point B, we have a turn that leads into point C, and eventually the end of our roller coaster. The theoretical speed at point C was determined to be 0.5 meters per second. However, the actual speed at this point was 0.07 meters per second. Clearly friction has done a large amount of work on this little marble. Since friction is equal to MAD, also known as mass times acceleration times distance, we were able to find the amount of friction being done by multiplying the weight of the ball times the average acceleration of the ball times the distance of the track to find that the average amount of work being done by friction on the ball was 0.125 joules.
This is pretty much the roller coaster, and when the cart is at the top of the loop, there's gravity, force normal, and centripetal force acting upon, and force push, whichever the direction of the cart. And then when it's in a turn, it also has centripetal force because it is in a half circle, so it has centripetal force, force normal, and force gravity, and force push. This is our roller coaster, and our overall design is that we'll have the most potential energy up here that will give us enough kinetic energy to go through the loop and get a turn to reach here. And before this, we were thinking to put another hill up here, but then it wasn't able to go up the hill because it didn't have kinetic energy to go up the hill. So we compromised, and also the turn was too wide, and sometimes it would fall off. So we made it more tighter, so that it would have less leg to go around, so that it can the marble can reach the end 100% of the time. And some errors we had in our lab is...
So, the thing is, you see this part right here? It's kind of cut off because we did a pretty bad job of just gluing the things. Well, not gluing, but putting holes through it for the photo gates. So this kind of slows the ball down, and it'd be really hard for us to find how that slows it down, much that slows it down.
Would you say that's a lot of friction?
It wouldn't really be friction, it's kind of just getting stopped by something.
Facts.
And also just this little spot right here with the glue, there's like a little bump there. Although it doesn't really affect, look there. And it'd be really hard to calculate like how much this stops the ball. But the thing is, overall, it doesn't really affect a roller coaster because the ball will always go through 100% of the time because of our expert roller coaster design.
Yes, sir.
We also had trouble with calculating the exact length because of the loops and the curves, and also how much friction it would have because the material is not very measurable, and yeah.